Welcome PCS members and friends to our today's seminar, which will be presented by Peter Karpov. So I would like to ask our scientific host, Dario, to introduce our speaker. Please, Dario.
Okay, thank you, Tilen. It's a great pleasure to have today Peter Karpov from Max Planck Institute in Dresden. So let me introduce a bit Peter. So he got his PhD degree in 2017 from National University of Science and Technology in Moscow with a thesis whose title was Induced Superstructures of Charge Topological Defects in Low-Dimensional Systems. And after that, he moved as a postdoc and he got this prestigious fellowship, this Alexander von Humboldt Fellowship. And he moved, as I said, to Dresden, where now he's working. And his research interests cover several topics. Among them, probably one of the main topics is probably many-body localization. And today he will give a talk about disorder-free localization in an interacting 2D lattice gauge theory. So Peter, please, you can start.
Thank you, Dario, for kind introduction and for inviting. So yeah, hello everyone. Greetings from Dresden. And without further ado, let's start. So the upshot of the story I will tell you today is that, you know, in many quantum spin models with disorders, there exists a phenomena of many-body localization. Although, well, it exists or not, it's a really very debatable question. So it's debatable in 1D also, and in 2D even more debatable. And yeah, the reason is that in 2D it's even more like hard because yeah, two-dimensional interacting systems are really hard to study. And here we consider actually one of alternative mechanisms for localization, which is called disorder-free localization. And here in this work, we show to our understanding for the first time that there exists a mechanism which is extremely stable and it exists for two-dimensional and interacting systems, providing localization phenomena. Okay, so let me first recap like usual scenarios of ergodicity breaking. So two well-studied scenarios are integrability and disorder. So if your system is integrable, yeah, it means you have some conserved quantities, integrals of motion, and number of integrals of motion is equal to number of degrees of freedom. So in this case, we call system integrable. And in this case, system will break integrability. Another very well-known scenario is disorder. So namely, if you have disorder and interactions, then in principle, you sometimes even can introduce local integrals of motion, and you also can break ergodicity. So here is an example of experiment actually from the Bloch's group, so which claims that experimentally they observe this many-body localization in this two-dimensional system. So what they do, they create, they have some like cold atomic gas cloud, and then create an imbalance. So they populate this left side of the circle and not populate this right side. And then they observe time evolution of the thing. And then after a long time, well, long experimental time for their measure, they see that this imbalance still preserves. So this work claims that many-body localization actually exists in two dimensions. Although there are very good theoretical arguments why it shouldn't. And actually what I'm going to tell you about is this third way of ergodicity breaking, and namely ergodicity breaking due to local constraints, and also known under the name of fragmentation of Hilbert space. So here in this scenario, the main thing is that there exist also some local constraints, or some local integrals of motion. But unlike this first scenario of integrability, number of these local integrals of motion is smaller than the number of degrees of freedom in the system. So system is pretty constrained, but still there is some freedom remaining. So it means that in principle, Hamiltonian will be block diagonal. And as you will see shortly, this block diagonal nature can also lead to localization phenomena. I forgot to tell, so please, if you have questions, you can just interrupt me straight away. Okay, so
yes, we have a question from Alexei.
Go ahead.
Yeah, sorry. I have a question exactly regarding this slide. So how does the whole story with integrals of motion, I mean, in principle, for the disordered many-body localization, you also have the local integrals of motion. And to the best of my understanding, there's as many as the degrees of freedom.
Right, exactly.
So, I mean, essentially, my take of the whole ergodicity breaking is that so far, all the known examples, they always had some sort of either explicitly present integrals of motions or emerging, like, hey, say in the disordered MBL, but you always have an extensive set of integrals of motion.
Well, fair point. So here in this disorder scenario, like in certain 1D systems, it is proved that there exist these local integrals of motion. Well, in 2 dimensions, it's not so easy. To my understanding, there is no any explicit construction of these local integrals of motion beyond 1D. Yeah, but yes, you're right. So generally, for all 3 scenarios, it is very typical to have at least some number of local integrals of motion. But maybe number can be smaller than total number of degrees of freedom, like here in this scenario.
Yeah, sure. Okay, thanks.
Okay, sure.
Let me ask you also an add-on. So in this version 3, which you are going, I guess, to discuss now in detail, in each of these fragmented blocks where you will now probably argue for some existence of MBL, is it basically because the can we view it that way that you mentioned that there is there is a number of conserved quantities which is macroscopic, say, but less than the number of degrees of freedom. Could we say that these act as some kind of effective disorder? Would that connect maybe to point to item number 2 in your list here?
Exactly. So you kind of foresee. So be with me. Like I think it's either next slide or next to the next slide.
Thank you. Thank you. But then I have the next question, which means that then still in each of these block Hamiltonians, H1, H2, H3, and so on, then there should be again additional integrals of motion.
Within each blocks, well, yes. It depends on the physicals.
In order to get indeed true MBL in each of them.
Well, so it's the same story, I guess, like with this 2-dimensional disorder-induced many-body localization. So, well, they might exist, but we don't know, well, how to construct them at least. So, yeah, but yeah, fair point. So it might be true, but just we don't know. And this holds both for the second scenario and for the third scenario.
Okay, thank you.
Okay, sure. Okay, but now I actually move to this idea. Yeah. So kind of this effective disorder. So yeah, so as I said, constraints lead to block diagonal nature of Hamiltonian. Okay, so let me number so this index Q will correspond to just this 1, 2, 3, just number of block of my Hamiltonian. And yeah, if I can solve my system within one block, so this CQ lives within certain block. And then in principle, I can construct some superposition over these sectors. Yeah, they call them usually super selection sectors. Yeah, with some amplitude CQ. And then when I start evaluating some observable for this state distributed over many sectors, well, so then I use just usual formula. So this mean value is just psi op psi. I substitute this guy here. And this is what I get. So this is time-dependent value of this observable. And then I immediately see that I kinda find an effective average of these quantities with respect to these weights. The weights correspond to just weights of given sectors. And it means actually, so as Sergey was already outlining 1 minute ago, that these kind of sectors in this business play a role of effective disorder. Although Hamiltonian in principle can be homogeneous, and the state itself is also homogeneous. And as we see shortly, this in principle can lead also to localization phenomena. Okay, and let me just mention, concluding this like introductory parts, a couple of works. So this is like the whole, well, actually this third way of ergodicity breaking due to local constraints. Now it's perceived as a new paradigm of ergodicity breaking, and actually many interesting models with interesting physics are being studied. So just to give you like a couple of examples. So they've been observed phenomena of slow relaxation in models like quantum dimer model and quantum East model. They've been observed quantum body scars in the large family of PXP model and like. They've been observed. There are quite a few already this interesting model dipole conservant models. So, for example, this fractonic quantum circuit model. So, like, I understand that this guy Raul will give a talk in a couple of weeks here, and also models coming from so-called tilted lattices. So, in the recent workshop here on thermalization, we had a talk from Frank Pohlmann on this topic. There is this pretty like recent developing. Okay, I guess you guys like know it very well. So flat band scenario for many body localization. So ECS team like produced recently a couple of very interesting works here. And finally, this is what will be closest to what I'm going to tell you. It's this disorder-free localization due to gauge constraints. So let me mention just a couple of works here. So previously, people studied either one-dimensional models, one-dimensional interacting, or two-dimensional but non-interacting. And they demonstrated for these models that gauge constraints can lead to localization phenomena. So what I'm going to tell you is what can happen now in 2D and interacting model. So this is in principle hard thing. Two-dimensional quantum models are hard to study. And yeah, as I said, to our understanding, we for the first time in this business of disorder-free localization due to gauge constraint demonstrate that like MBL can exist.
Peter, we have a question from Alexei. Please, Alexei.
Yeah, I mean, it's a simple, perhaps, could you say a bit more? I mean, the slow relaxation part, so they don't really observe clear signs of MBL, or they're just, they have finite size effects that, I don't know. I mean, I'm mostly interested in the quantum East model. This is actually related. I have a second question. So where do, say, quantum glasses, do they fit into this local constraint picture at all? Because East model was developed by people in the glass community precisely to have glasses without disorder. And for some time, I was thinking that all these glassy models without disorder would be a natural hunting ground for MBL without disorder, for disorder-free localization. So,
right. Okay. So to my understanding, yeah. So here in these types of models, yeah, the point is that due to constraints, you have very funny connectivity of your Hilbert space. So, for example, unlike transverse field Ising model, where your connectivity of your Hilbert space is just a hypercube. So here it's like far from that. And this funny connectivity can, well, it can be either, so either your Hilbert space can be still connected, like every point is connected via some path with every point. And this is actually like, so for this model it holds, or it is disconnected. This is what I'm gonna tell you. So it can lead to localization or just to slow relaxation just due to this very funny connectivity. Right. But for this model, yes, there is no true localization. But yeah, you're right. So this is very related to this glassy phenomena. And yeah, well, actually, I guess it's pretty the question of time scales. So like, yeah, so these glasses, of course, yeah, they in infinite time limit, they are ergodic, but in practical observation times, they are not. And in principle, in these models, yeah, so they become non-ergodic. Sorry, they become ergodic, but only on very large time scales.
Okay, thanks.
Okay. Okay, so now let's move on. So yeah, outline. So this was like pretty lengthy introduction. So let me just speed up a bit. So what I'll tell you in the remaining part of the talk is I introduce concretely the model we study, this two-dimensional quantum link model. And two pieces of result I will show is this study of quantum dynamics via this method of variational classical network we introduced. And another funny thing, I will show you this classical arguments like unconventional percolation argument that localization exists. Okay, so let's go. So the model I study falls into the class of this so-called lattice gauge theories. So yeah, why they're interesting to study? So first of all, they are like fundamental theories of matter and fields, where local constraints, local symmetries induced by just this Gauss law impose constraints of the system. And recently they drew a lot of attention because, okay, if you put this gauge theory onto the lattice, so first of all, they become amenable to some numerical solutions like what I will show you, and also to quantum simulators. And just this kind of, okay, so this is like the basic setting. You have a lattice, your matter field lives on sides of the lattice, and your gauge field will live on the links of the lattice. And just, okay, so this is just example of recent, okay, 5 years ago already, it has been demonstrated how to, using digital quantum simulator, simulate one of the models, so-called Schwinger model. And this is also recent proposal from group of Marcello Del Monte, who also gave in the recent conference a very nice talk. So this is related to the fact that in 1D, one can map certain Schwinger-like models to PXP-like models. And then one can study, for example, using this already kind of bit famous 51 Rydberg atom simulator in Lukin's group, for example. So this is already like in principle directly studiable these days. Okay, so concretely, why I will consider this quantum link model, which is specific lattice gauge theory model. So it was introduced by Visa back in 1997. So this can be thought as a simplified version of lattice quantum electrodynamics. So if you want to write your true quantum electrodynamics on lattice, then you have, in principle, your photonic degree of freedom, which is like infinite ladder of states. So what they do here, they consider super simplified version. They cut off the whole ladder of states just to two bottom levels and model the gauge field like photon with its simplified version, just spin 1/2 degree of freedom. And the model is interesting because it's related to many different models, like quantum dimer model is just a particular case of this quantum link model. Also, it's related to quantum spin lattices, as you will see, and quantum spin lattice. And okay, so this is like the picture of what I will study. So this SZ, spin 1/2 SZ degree of freedom. So SZ will be, can be thought like electric field produced by some charges. So actually here in this work, I will consider even further simplification. We will not have any dynamical charge degrees of freedom. So we will have only fields. So it's even more simple model. And already this simple model has some interesting physics, as I will show. Okay. So yeah, concretely, okay, so this is like just configuration. So I consider spin 1/2 degrees of freedom, and the convention will be like this. So if my spin points to right or to up, it corresponds to spin plus 1/2. And if my spin points to the left or down, it corresponds to spin minus 1/2. And it will be important to introduce this these plaquette operators. Okay, so let me explain the notation. So if I have this plaquette, I number my spins 1, 2, 3, 4, and then this U plaquette is just a plaquette like flipping operator. So S1 plus, so S1 plus is a spin raising operator for this link 1, and so on. And you see that what this operator does. So if my plaquette was oriented, say, clockwise, like here, after applying this operator, it will be oriented counterclockwise, and for U dagger, vice versa. And if plaquette was not oriented, either clock or counterclockwise, then applying this operator just kills the state and gives you 0.
We have another question from Alexei.
Go ahead.
Yeah, sorry, very simple one. I guess things are independent on how you identify links and spins. I mean, so far you made it so right and up is spin up, left and bottom is spin down, but of course you could have chosen any other assignment. I guess this would only affect the how we define the flip operator and the plaquettes, which
Right.
Yeah,
you're
okay.
Right. Yeah, there is kind of asymmetry, but yeah, so this definition is related, yeah, to this.
Well, I mean, what I mean is, no matter which, I mean, you can basically assign things at random. I mean, you have 4 configurations. You have 4 link directions. And you need to assign them to 2 possible spin values. So no matter which assignment you take, basically you can always define more or less the same Hamiltonian and get the same result. That's what I'm curious about.
Okay, if I understand the question correctly, I think you are right.
Okay. Yeah. Thanks.
Okay. Sure. Okay. Yeah. Okay. And right. So using these operators, yeah, this is Hamiltonian we construct here. So okay, let me just quickly tell why it's U1. Yeah, lattice gauge theory. So I can introduce like some exponential factor like e to the minus I phi in each vertex, and then I will immediately see if I do this that if I do it properly, that my U plaquette operator will be invariant with this vertex transformation, and then yeah, so this is why it is this U1 quantum link model.
Peter, sorry, we have another question from Ihor. Ihor, please unmute yourself.
Hello.
Hello.
I'm a bit confused about the structure of the Hilbert space. So here, is it many bodies? So yeah, could you please specify?
What do you mean by structure of Hilbert space?
So is it a many body or single body system?
Yeah, well, so it's system of many spins. So you have so each spin 1/2 lives on link of the lattice. So you can think it's like, well, kind of you have not your quantum Ising model, but some kind of fancy spin model with many spins. So in principle, it falls in the class of some kind of fancy many body quantum spin model.
I see. And the summation is over every square.
Okay. So this I didn't yet tell. So yes, exactly. So this is yeah, right. So this is my Hamiltonian. So a summation is over each square, each plaquette, where I apply okay, either this what I call kinetic term. So this guy just tries to flip my plaquette and kills the state if it's not possible. And this guy, what it does, it flips plaquette twice. It tries to do it twice. So if it can flip plaquettes and then flip it first in one direction and then backwards. So it means that this guy will either also kill the state or return well. So this basically guy just returns whether your plaquette is flippable or not. So this is potential term. So this term is diagonal. So this guy counts just number of flippable plaquettes in your system. And this guy actually performs the flips themselves. Okay. Okay. And
we have One more question from Alexei.
Yeah, sorry for interrupting you.
Yeah, no worries.
I mean, the two terms of the Hamiltonian, the kinetic and the potential one, they commute, isn't it?
Yes.
So then why you're saying that the kinetic term, I mean, you said the potential term is diagonal. That to me sounded like that the kinetic term is not. So
Okay. Let me tell precisely. So each of these guys, if you don't perform the summation, each of these guys correspond commutes to its correspond.
The points they I mean the same on the same plaquette they do commute, but not on the different.
Right. So okay, they commute on either on the same plaquette or if plaquettes are separated. But if two plaquettes share a link, then they don't commute. Yeah, all fine. Sorry, yeah. You are completely right. So this is the only scenario. So they almost every time commute with each other, except only one case when they share one link. Exactly. That's good points. Thanks. All right, and we can introduce also these charge operators. Okay, so let me in simple way. So these charge operators will be conserved charges. So they will commute with both Hamiltonian and with themselves. And let me just in simple words, so this is a formula, but let me in simple words tell you what these charges are. So for example, let me consider this red point, this +2 charge. So you can think, so once again, you think about these arrows like your electric field and this charges like, well, electric charges producing this field. So for example, here the counting is follows. So I consider I just count number of arrows going outwards. And then, this is like spin 1/2, 1/2, 1/2, 1/2. I sum all of them. And then I get 1/2 times 4, which is just 2. And this is my charge 2. And the same game I play. So for example, like this charge, I have 3 inflow arrows. So 3 times -1/2 plus 1/2 give me this guy is charge -1. And these guys are conserved charges. So this is, well, if you think for a couple of seconds, you will immediately realize it. But for example, okay, let me consider this charge, this one. If I flip my plaquette, then I revert one incoming and one outgoing arrow, and then the total balance is just preserved. And it means that all these charges are these local conserved quantities, which will be important for localization phenomena. So these are these local conserved quantities. And actually, so in what follows, I will consider different charge sectors of the model. So for example, there exists this what we call fully flippable sector. So basically just a 0 background charge sector. So you can think that you arrange initially this configuration of checkerboard like flippable clockwise, counterclockwise plaquettes, and then you construct the whole sector of Hilbert space corresponding to connected to this configuration. And this is pretty similar to spin ice model because you see this is like this famous 2-in 2-out rule, very typical for spin ices. Yet another sector, if you consider checkerboard alternating plus and -1 charges, this actually is exactly mappable to a quantum dimer model. So quantum dimer model is nothing else but particular case of this quantum link model corresponding exactly to this distribution of background charges. And in principle, you consider some other like more or less random charge sectors, so which have many charges, and this random charge sector. So important thing is that these charges are so-called static charges. So they are not dynamical, they cannot move, and they just preserve this background. And then this is exactly the point. So if we start averaging over all sectors like this, like that, like this, all the random sectors of the model, then this average over sectors represents actually effective disorder average over distribution of these charges. So these charges will play for each given sector a role of effective disorder, even though that the total system, like total Hamiltonian, do not have any like imperfections, any impurities, and if your initial state also doesn't have any like inhomogeneities, then still it's possible to observe localization. And now I guess I will move to.
Do you have a couple of questions? do you have a, let's say, a counting of how many states you have in a given sector? So I mean, if I understand, the sector is given by all the set of charges for the full lattice, right?
Right. Okay.
And then you can count which states belong to that sector. Do you have any idea of, let's say, the scaling, or let's say, you know, for example, in PXP, you know, given a sector, you know how many states are there.
Right.
You have the Fibonacci. I was wondering if here you have something similar.
Yes, for sure. So, okay, a couple of points. So, okay, to be precise, there are conserved charges and conserved fluxes. I omitted for like simplicity of the discussion, so it's a bit more complicated than that. Yes, sure. For this, so these sectors are well known. For example, the dimer sector. Yeah, you just know like there exist like very well known formulas for number of states in such a sectors, and also for fully flippable sector. And yeah, like the law is like e to the power area of the system. And in front of this area, it'll be some like numerical prefactor. So it's exponentially growing with the area of the system typically. Now, this is for these like clean sectors. But then if you start thinking about this disordered sector, it very heavy depends on concentration of your disordered charges. So in principle, you can easily construct such sectors that like just completely frozen. So these guys also exist. And then you can study what is like typical sector. So what will be the sector like typical? So I will show you what is the typical sector, like in I guess in 2 slides. And the typical sector is kind of non-trivial. So it's neither this nor that. So it can be interesting. Okay. Okay, I'll show you in 2 slides what the typical sector is. Okay, so now let me move on until we have some further questions. Okay, this I guess I will just mention very briefly. It's a technical point, and so we use just some specific methods for our quantum evolution. We also introduced it like pretty recently. This is what we call variational classical networks. Okay, so the basic idea is, well, time evolution of quantum system is generically a hard problem, and this is partially due to the fact that just storing the wave function with n degrees of freedom requires you storing these 2 to the power n amplitudes. And the idea, like in many these neural network methods, is try to generate on a flight your amplitude. So you have your state S, you give it to some machine, some algorithm, and then it produces some psi of S. So you don't store this huge amount of numbers. You just store this kind of state of this machine, which gives you the number. So in our case, we use some particular ansatz based on perturbative expansion of the wave function, more precisely on the cumulant expansion. So this is like somehow fancy version of perturbation theory, which actually, but unlike usual just whatever, like the first order, second order perturbation theory, you re-exponentiate your perturbation theory, and then in many cases it can work like well beyond like direct applicability. So this is basically the limits where we work in. So this kinetic term will be much smaller than this potential term, and this will concern the results I will present you next slide, this numerical results. But then I will show you that the phenomena is not only limited to this kind of case. Okay, and now key slide, my first key slide of the presentation, this results showing quantum dynamics for different initial states and observing different quantities. So what I show on this slide, I study 2 different initial states. So this is what I call X-polarized state, and another, this equal weight superposition of, let me explain step by step. So first, X-polarized state. It is just equal weight superposition of all to the power n states in the system, which can be written like this. So this is direct product so over all my links I. This is my like a spin plus 1/2 minus 1/2. And this is I call like X-polarized state. So if you start expanding, so this state will have actually, so it's kind of superposition of all possible sectors of the model. So you have actually very many charges here typically. So this is kind of most effectively disordered state. This is one guy I will study. And another guy, this also equal weight superposition, but only of states belonging to this fully flippable sector. So only this guy and all guy connected to this configuration, and then I consider this equal weight superposition. Right, so for this, the most like disordered state, yeah, we expect localization phenomena, and this is what we see. So we study, we perform the following kind of numerical experiment. So we take our two-dimensional system. So here a system is like 10 by 10 plaquettes. We take the state, and then on top of this state, we excite some excitation like column-like excitation. So here is like a schematic plot. So, okay, let me start from this inset. So D is just the distance from this like excited plaquette, and this is like just normalized energy density. So I have excitation in my column number 0, and then columns number 1, 2, 3, 4, 5 are not excited. And then I study how this non-uniformity propagates throughout the system. And this is what I see here. So, okay, so this epsilon D is a normalized energy of this column at time t. And this guy shows deviation of this energy from its initial value. And so this basically just shows like how my signal propagates throughout the system. So here I see like strong bending, which kind of already indicates a bit this localization scenario. Now, for this most clean state, so no disordered charges, this is what I observe. And so corresponding energy propagation plots, so we observe propagation of signal up to the largest distances in the system, like we have here. So even like this distance equals 5. So here you see like this just ordinary 1D plot. So we see the signal, unlike this case where we don't see any signal beyond numerical errors. So this already suggests that probably this state is localized and this state is ergodic. And what I'll show next, I'll present some additional classical argument why it should be so.
Sorry, what is playing the role of the, let's say, the disorder strength? I mean, in standard many-body localization, you say, okay, I have a certain disorder strength, and so the property of being localized or not of a certain state depend on the disorder strength. Here, what is playing this role? I mean, do you have an additional parameter to tune such that maybe one state in some cases disordered, in the other not?
Exactly. This I will show very soon in 2 slides. Okay. Yes. So one thing is that we have some tuning parameter, but unlike usual scenario of localization, we tune not parameter of Hamiltonian, but we will rather tune a parameter related to initial state. So this is not this is not conventional. Okay, I will show you.
Somehow you're working at fixed disorder. I mean,
Okay, I will show you. It will be
okay,
like
later.
Next numbers next.
Okay.
Yeah, okay. I will show you and try to explain. Yeah, so here you are right. So here we consider only kind of 2 strengths of disorder, like most disordered and least disordered, but actually we can tune in between. So I will show it. Okay, so now what I want to present is this. Okay, this is almost like final part of the talk. So now this key slide from this classical percolation, like an unconventional percolation argument, why you should have here for this model localization at all. Okay, so here I actually consider this most disordered state, and then I sample what is like typical, what is typical configuration. What is typical basis state, which contributes to this the whole superposition of all 2 to the power n states of the system. So you see that what I do actually, I just assign to all my spins either values +1/2 or -1/2, and then I just look what I have, and I look at the distribution of these charges. So for example, I have this like -2 charges, and what I can immediately realize if I will start quantum evolution of my system, this whole 2 by 2 block will be frozen just due to this -2 charge. Yeah, you see, so all arrows pointing inwards, and it means that all 4 plaquettes here can be never made either clockwise or counterclockwise oriented. Yeah, so this incoming arrows kind of do not let it to do it. And likewise for this +2 charges, you have this blocking. So you have in principle some very hard blocking, but by this plus and -2 charges. But also in principle you have many like 0 charges, many +-1 charges, and this +-1 charges, they also create some kind of constraints which are weaker, but you will see that they still play an important role. So what I will do next, I just observe which plaquettes are flippable, which are oriented clock or counterclockwise. So these arrows show this. And then I start the following classical procedure. You can think about just a classical infinite temperature Monte Carlo for just evolution and just counting the state. So this is here, it's actually a procedure to construct the whole part of my Hilbert space, which is kinetically connected to this given state I show you here. So this is what I do. If I can flip my plaquettes, I start flipping them randomly. And then I color those ones which have been flipped. And I do it, and I can continue this doing it. So for example, I can flip this plaquette, this one. Let me flip it. And I see after I flip it, then I have another plaquette which also became flippable. And I color, so by gray color, I designate all plaquettes which have been flipped at least once, which have been flippable at least once. And then I continue. Now I can flip this guy, for example. If I flip it, then this guy becomes flippable. And I continue the procedure. And I construct all plaquettes which have been flipped at least once. So this construction corresponds to just plaquettes which could be flippable. And this also, okay, so right-hand side exactly corresponds to this left-hand side plot. So you see the shapes are like similar. And here I just show, like in my Monte Carlo procedure, how many times each plaquette has been flipped. And I immediately see that there is like this funny thing. So I have this white regions. These are plaquettes which have not been flipped even once. And these are not only these like hard blocks. Yeah, you see, so for example, this hard block, this have not been, but also many of these guys never been flipped. And this is due to this, well, kind of very funny distribution of this +-1 charges and all other charges. So this is some kind of, well, this funny constraint coming from many of these charges. And you immediately see that you have some islands which are connected within one island, but then you in principle can have different islands which are disconnected one from another. And if you have such islands, then just classically, this is just a geometric argument which tells that these guys cannot communicate with one another. So neither classically by this classical Monte Carlo procedure, nor quantumly. And it means that if you excite some like signal, some energy density here in this island, it will forever stay here. It will not penetrate these guys. So this means that it hints that this is possible scenario of this localization, which is connected to either presence or absence of percolation of these flippable plaquettes in the system. Okay, and now, okay, actually final slide, and also hopefully will answer to Daria's question, what we tune here. So now we actually interested to study this percolation problem in a more detail. So what I demonstrated you so far was just this one state, like fully disordered. But actually we can tune between like most clean state and most disordered state. So what we construct, so we take this fully flippable state as like one helper, and this explored state as like other helper, and then depending of my parameter alpha. Okay, so I construct single parameter family of my initial states, and tuning this parameter alpha, I tune either to this like most disordered explored state or to this fully flippable state. And this is some formula, some particular formula. And here I present a plot which shows, okay, so this is this parameter alpha, just this guy, it shows just percolation of probability if I sample random state from this distribution and construct, as I outlined in previous slide, construct these islands, I immediately see that for small alpha, I don't have percolation, while tuning to large alpha, I have percolation almost once. So here's this non-percolating case corresponds to many islands separated by like C of non-flippability, while this case of large alpha corresponds to, well, you have like a single huge island where you have some small frozen kind of parts. And then you can tune between these two. Okay, so this is the key thing. This argument actually puts a strict boundary. So although like for quantum case, we could study only some limiting case, like kinetics are much smaller than potential term, but this argument shows that it doesn't matter actually what is the relation between kinetic and potential. So anyhow, we will have this boundary, just classical boundary on our quantum localization-delocalization. It means that in this side of the transition, system is ever delocalized, is ever localized, and either both classically and quantumly. But what happens in this side of the transition, it's a bit trickier to say. So like classical argument tells that it doesn't tell that the system should be localized, but still you have some imperfections. And actually in principle, so this is kind of the most hard to study, this vicinity of this percolation threshold and nearby this percolation threshold. So actually we understand that probably true quantum value of the transition should be higher because you have this, well, imperfections here. And then you have some destructive interference. And then probably like true quantum value of the transition will be higher than this classical, but at least we can put this strict boundary.
I don't think that this is the corresponding of varying the disorder. I mean, to me, it looks more like, in standard MBL, suppose that you have a mobility edge. So somehow you have a portion of the eigenstates which are, let's say, localized and the portion which is not localized. And to me, it looks like that you are moving through crossing the mobility edge more than changing the disorder strength. Like, to me, yeah, it looks more an interpretation like that you are, let's say, moving through the extensive quantity that control the mobility edge, which can be the energy or the density or whatever. And by adjusting that, you move from, let's say, the part which is localized to the part which is, do you agree with this interpretation?
Yes, I think this is in principle fair interpretation. So yeah, well, the main point of the work was actually to demonstrate phenomena of localization in such type of model. So this was the main, because it was not known. It was known that in 1D, yes, in this lattice gauge theories there exists localization. It was known that in 2D free fermion theories it also exists. So it was not known what's going on for 2D and interacting such kind of lattice gauge theories. So the main point was to demonstrate localized regime. So this is demonstrated. Now, yes, I agree that there can be different interpretation. I totally understand your point of view, and so yes, you can think like this. I think it's a perfectly fine way to think about it. Okay, so let me just conclude, and maybe you can ask some other questions. So yeah, here is like the summary of the talk. So here, as I told, we demonstrate that particular lattice gauge theory with homogeneous initial state and homogeneous Hamiltonian can become non-ergodic, and we put so we studied both like quantum evolution, and we put some classical unconventional percolation argument boundary onto this localization-delocalization transition. It's interesting that like recently people proposed to realize something like this, like quantum link models with this Rydberg arrays, and hopefully, well, in some future we will see some also experimental data on that. Yeah, that's it. Thank you.
Thank you, Peter, for your excellent talk. Let us thank our speaker. We are good with time, so we have enough time for questions. So, Alexei, please.
Yeah, I have several questions. So perhaps one, how things would how stable are these results with respect to the exact geometry of the model? So I was thinking, say, if instead of square lattice, you will take kagome or say honeycomb. You can still define a similar link model, although say on kagome, well, there might be slight differences, but do you think things would still work? I mean, I'm mostly thinking that this percolating transitions are a bit different depending on the geometry of the lattice. So I'm curious whether this can have any significant effect on your conclusion.
Right. Okay. I expect, so this is what we studied, like this only this is what we studied, but I expect that, well, you know, like, so for example, like for quantum dimer models, they've been studied in many different lattices, including Kagame lattice. And I expect that, yeah, like, of course, probably I can imagine that value of the transition will be shifted, but I still expect that it will be there. And also expect that if we go so to say three-dimensional systems like cubic or whatever, like three-dimensional, it's also should stay. So
yeah, because they also have the percolation transition. Okay, and the other question is, what happens if you allow for the charges to move, or perhaps a related question, what happens if, yeah, I do not have any exact mechanism in mind, but, you know, I'm thinking can you incorporate into your construction this argument that people put forward to say there's no MBL in 2D, that you can get regions that act as paths for the rest of the system. So I guess there should be a way to, probably these are to allow the charges to move. So can you incorporate that? So my expectation would be like, did you try looking at what happens if you just allow maybe one charge or a few charges to move, what effect this would have on the on this whole freezing? Right.
Yeah. Okay. So actually, this is what we are doing right now. So we're studying this problem with dynamical charges. Yes, there are like different aspects of this question. So for example, yeah. Okay. Let me think. So first of all, yes, probably if we allow all the charges to move, then I think, yeah, probably this will be enough to break localization, to have ergodicity. And now it will be a bit, well, similar. So like if you have these charges which are heavy, so here in this picture, you can think like infinitely heavy charges. So charges are infinitely heavy. Yeah, then you have localization. Then if you start decreasing your mass of the charges from infinity to some smaller values, yeah, so I expect that for some finite, like large value of mass, probably a system will be ergodic, but now like time scales of restoring ergodicity will be very huge. So this is probably somewhat similar to this glass setting, I think. So that's, at the end of the day, my feeling, although we don't know it yet, is that if you allow these charges to move, then probably you will also not have true localization, although you can have very like long time scales. And second question, yeah, if you have say one charge or two charges moving, yes, this we actually tried. And okay, see, so if you now this depends where you put one charge. So for example, if you put here your dynamical charge, and then it's kind of constrained. So okay, so your charges. So the rule for the charges is as follows: if you have a charge like dynamical charge, it can move along the link only in the direction of arrow, and then it flips the link. So if you put your charge like here, then it will be like frozen also. So it's like bounded. And now it means that, yeah. So if you add very small, like some small concentration of charges, at least some of them will be like, well, confined. So yeah, or at least in some realizations of this initial distribution of charges, you still will have, yeah, this localization.
Yeah, I would like then to make just a small comment. You might be, I might be interested to know, people in the glass community, they studied a similar problem. So they were basically trying to see if you can induce glassiness by sort of pinning a fraction of the particles in a system. And they were trying to see how many you need, how big a fraction you need to pin to get a glass. And right. I think they found the transition at a finite fraction. So I'm actually curious, is there any relation, or can you use these results would these results matter in your context or not?
Right. Yes. So this is actually also what we try to do right now. And yeah, we understand. So if we construct the whole phase diagram say we have like two parameters to tune this alpha, which is kind of concentration of frozen charges, of background charges, and some parameter beta, which corresponds to concentration of your dynamical charges. Then in principle, you can construct the whole phase diagram, and we expect some line in this phase diagram. So yeah, I think you're right. So if you tune your concentration of dynamical charges, starting from, say, this state, then you increase number of your dynamical charges, then probably you also observe some kind of percolation transition. Although now it's funny enough. So here you will have for these charges you will have link percolation, bond percolation. Although for plaquettes you have like this, side percolation. So it's somehow, yes, two percolation problems become intertwined. And this is a funny thing to study.
Okay, yeah, thanks.
Yeah.
Do we have any further questions or comments from the audience?
Yeah, maybe something that somehow simulate disorder is exactly like if you let the charges move, they somehow can create connections that in the previous configuration were forbidden, right? I mean, so I was wondering if you can do, let's say, a situation in which somehow you are in a localizing situation, but then charges start to move a little bit, and this can induce a transition to the ergodic side because they create new, let's say, new connections, and they connect the islands. So somehow that kind of disorder is, in a sense, playing the opposite role that plays in standard MBL, right? I mean, typically in MBL, the disorder is what induces localization. Here, instead, this kind of, let's say, impurities that are moving, in a sense, they will make the system more ergodic. I'm wondering if it is a situation that it is easy to simulate and to see how the mobility of the charges can change the situation.
Yeah, well, okay. I guess it's a bit related to question of Alexei.
Right.
Right. No, so totally. So yeah. What to add? So, right, you're right. So yes, if you now allow charges to some dynamical charges, they will flip some links, and this generally, will have some plaquettes flippable.
Am I right? I mean, the more charges you have, and more the geometry is constrained, right? So if they move, okay.
Right, exactly. So more more static charges you have, more constrained you are, more dynamical charges you have, more like free you are. So yes, exactly. So if you start from the configuration like this, which has many static charges, and start adding bit by bit dynamical charges, then you make system more ergodic. That's for sure. And then we expect that by tuning now concentration of dynamical charges starting from 0,
right,
at a given static background charge, you will probably have also some percolation transition.
Right. So you can have, let's say, a phase diagram which is more extended, and
exactly, right. Yeah.
Do you think this is a generic feature? I mean, somehow with this example, you told us that disorder is just, let's say, the fact that you have sectors. So do you think generically you could always, let's say, embed disorderly systems in larger systems where disorder comes from averaging over the sectors?
Good and very tricky question. I don't know. So, so I mean, how generic it is, I can tell you that what's kind of one of the limiting factors is that we have to have finite local Hilbert space. If we have finite local Hilbert space, then in such kind of models, we will have transition. So we'll have this like percolation threshold. Now, if we go to through this, like say quantum electrodynamics, like infinite local Hilbert space, then this just disappears because now every plaquette is flippable all the time. So you don't have anything like this. So this is, so how generic? So it is generic, pretty generic for systems with finite local Hilbert spaces.
May I comment? I would even say so. Yeah, we have a recent manuscript with a very similar physics. I think, you know, actually, I'm very surprised. So I saw your paper, Carl introduced me, but I didn't read in detail. And now, after listening, I would say that the physics that we observed there is basically exactly the same as you see in this system. So we consider the different class of systems, and yeah, I would say exactly same phenomena. And while we worked with the local fermionic states, I'm pretty sure that in that particular case, one can find similar percolation transitions during a macroscopic number of local constraints, even for bosonic states. We can discuss later in detail if you want. But I would say, yeah, that very possibly even for infinite local Hilbert spaces, it's possible.
Okay, this I don't understand, so maybe you explain later indeed. Yeah, surely we know this works. So we discussed it actually with Carlo, and yeah, okay, of course I know it. And I think it's great. So this also like adds a bit to the point how generic it is. So yeah, probably it's well, yeah, it is kind of generic. And yeah, I'm happy to know this.
Okay, we have another question from Alexei.
Yeah, this basically a bit continues on where, well, related to the question of Dario. So did you consider generalizations? Essentially, from my understanding, the key argument here is that you get a mapping to a percolation problem. And from that, you can tell that at least in some sectors, you inevitably get frozen dynamics. So is that correct?
Right.
So I was curious, I mean, because this potentially, you might think that you might now take percolation transitions and try to construct, like to go backwards and try to see if you can construct a quantum model. So in particular, I'm thinking of something that potentially would give a very fancy non-ergodic transition. So have you ever heard of explosive percolation?
I did, yes, I have.
Yeah, so I'm curious, I mean, did you consider generalization in that direction? So for example, trying to see if you can get models with, so starting from explosive percolation, get a quantum model where you have the same argument, because then, if I understand correctly, as you would approach that explosive percolation transition, so it should be definitely a different class of ergodicity breaking, I think.
Right, sure. Okay, regarding generic idea of this like reverse construction, so you have classical model and then you construct quantum model. So to large extent, I mean, people knew, for example, with dimer models, they had this classical dimer model for ages, and then at some point they can start considering these quantum dimer models. And so for classical, it's like all like 50, 60 years of like results and some exact theorems. So these people do in principle. And I think this is, probably one of interesting ways to go here. Regarding explosive percolation. Yeah, well, okay, it was like a bit of a buzz like 10 years ago or so with this explosive percolation. So people thought that it's like first order phase transition, but I understand that at the end of the day, it turned out to be still second order phase transition, but very, very sharp. So probably, yeah, so it will not be like some, well, completely different physics, I would say. But yeah, okay, we thought in this direction. So yeah, we didn't do anything, but this is a cool question to ask. I don't know. This is a cool question to ask, whether it's possible to construct some quantum model corresponding to explosive percolation. I think this is...
I mean, you apparently know that better than me, because I still thought it was first order.
Okay.
What I meant is that perhaps there might be other percolation transitions out there, and which might be worth checking. And then the question is, can you turn your construction into really generic, like quantum non-ergodic models on demand? So you just give a percolation setting, and from that you construct a model, and for which you can tell at least something beyond just a naive exact diagonalization.
Right.
Methods.
Yeah, I mean, this makes perfect sense for me. Yes. So yes. I think, yeah, this is promising.
Okay, thanks.
Okay, do we have any more questions from the audience? In case not, then let's thank Peter again for his excellent talk. And with this, we conclude our